Galaxies are crashing into each other right now. These violent galactic collisions are not random disasters, but the universe's primary method of creation, forging new worlds from absolute chaos. By the end of this, you will understand how our own cosmic home was likely born from such an event and what our distant future holds. We will uncover how these titanic encounters can ignite billions of new suns and whether our solar system could survive one. What do you believe emerges from the universe's most violent chaos? Hundreds of billions of stars are now caught in a slow, inevitable dance. Picture two majestic spiral galaxies, each a whirlpool of suns and cosmic dust, drawn together by an unseen force. They do not rush headlong into a fiery crash. Instead, they begin a gravitational embrace that unfolds over hundreds of millions of years. Long before the galaxies truly merge, their mutual pull starts to warp their perfect shapes. Immense tidal forces stretch out vast streams of gas and dust, creating luminous arcs that streak across the darkness like the braids of a cosmic giant. These are tidal tails, beautiful and destructive ribbons that mark the beginning of the end for the galaxies as we know them. This is not a collision in the way we think of two cars crashing. It is a gradual, relentless rearrangement of an entire cosmos on a scale so vast it defies human comprehension. Astronomers use some of the world's most powerful computers to simulate this celestial ballet, watching as the gravity of each galaxy twists and contorts the other, pulling their spiral arms out of shape long before their cores ever meet. To witness such a simulation is to watch a dance that lasts for eons, compressed into mere seconds, a humbling reminder that the universe works on a timescale we can only model, never truly experience. And within this beautiful, slow-motion chaos, the seeds for entirely new worlds are already being sown. This initial gravitational embrace begins to rewrite the very anatomy of each galaxy. As they draw nearer, their mutual gravity starts to sculpt the cosmos. The beautiful spiral arms, once orderly and distinct, are the first to surrender to the chaos. They are pulled and stretched into vast, luminous streams of gas and dust. These are the tidal tails and bridges, cosmic filaments that can stretch for hundreds of thousands of light years, physically linking the two galaxies long before their cores ever meet. It is as if the universe is drawing a glowing path between them, a highway of raw material for what is to come. Within these colossal streams of gas, something remarkable ignites. The same gravitational forces that are tearing the galaxies apart are also squeezing the vast clouds of hydrogen and helium that drift between the stars. This compression is like a cosmic trigger. When these gas clouds are jostled and compacted, they collapse under their own weight, sparking the furious birth of millions of new stars. Suddenly, the dark galactic outskirts are set ablaze with the brilliant blue light of stellar nurseries. A single gravitational pass can light a firestorm of star formation across entire galactic hemispheres. This celestial dance is rarely a single event. The two galaxies, locked in their gravitational waltz, often swing past one another not once but several times. Each close encounter acts like a whirlpool-stirring spoon, churning the interstellar medium and amplifying the distortions. With every pass, more stars are flung onto new, unpredictable orbits, and more gas is compressed to ignite fresh waves of stellar fire. This prolonged perturbation is the essential prelude, the universe setting the stage for a far more intimate and violent union. It proves that even at a great distance, gravity's subtle tug can initiate a chain reaction that will ultimately forge an entirely new cosmic entity from the wreckage of the old. This beautiful chaos is merely the prelude. the galaxies now plunge toward their final, violent union. Their cores, each a dense concentration of stars and a hidden supermassive black hole, swing past one another in a cosmic slingshot. They may not collide head-on. Instead, they engage in a breathtaking gravitational maneuver, whipping around each other and trading momentum in a way that sends shockwaves through their remaining structures. The orderly rotation that once defined these spiral islands is shattered. Stars are flung from their predictable orbits onto wild, chaotic paths. Some are cast out entirely, becoming lone voyagers in the cold emptiness between galaxies, destined to wander the void forever. At the very heart of this turmoil, the true monsters awaken. The supermassive black holes, once dormant at the center of each galaxy, are now stirred by the incredible influx of gas and stars. Drawn by friction and gravity, they begin their own slow, inexorable spiral toward the center of the new, combined galaxy. As they drift closer, they funnel colossal amounts of gas toward their event horizons. This material doesn't just vanish, it spirals inward at near light speed, heating up to incredible temperatures and unleashing blinding flares of radiation that can outshine every star in the galaxy combined. For a brief, brilliant moment, the merging galaxy can become a quasar, a beacon of raw power visible across the universe. Meanwhile, the interstellar gas clouds themselves are not spared. They slam into each other at phenomenal speeds, generating violent shock waves that ripple across light years. These waves heat the thin medium between the stars to millions of degrees, causing it to glow in high-energy X-rays. The entire system is racked by extreme turbulence, a celestial firestorm that appears utterly destructive. Yet this apparent destruction is a cosmic illusion. The intense heat and pressure from these collisions, the very forces that seem to tear everything apart, are also forging the heavy elements essential for new kinds of worlds. The violence of the merger is not an end. It is the necessary, fiery crucible from which an entirely new galactic structure will be born. Out of the violent chaos, a creative firestorm erupts. This is the starburst, a period of frantic, almost reckless star birth that can outshine an entire galaxy. The same gravitational forces that are tearing the galaxies apart are also performing a miracle of compression, squeezing the colossal reservoirs of hydrogen gas scattered throughout the galactic disks. Where there was once a quiet, diffuse nebula, a single cloud now collapses under its own immense weight, fragmenting into hundreds of dense knots. Each knot ignites into a new sun, flooding its surroundings with fierce, young light. In a starburst, this process happens on an unimaginable scale, not one star at a time, but thousands, even millions, all in a cosmic blink. A region of space that was dark for billions of years suddenly blazes with the brilliant blue-white glow of stellar nurseries, burning with an intensity that can be seen across the universe. Look at the antennae galaxies, a pair locked in a spectacular embrace. Images from the Hubble Space Telescope do not just show two galaxies merging, they reveal a cosmic fireworks display. Scattered across the tangled wreckage of dust and stars are countless brilliant blue knots, each one a massive cluster containing thousands of newborn stars. These are the nurseries for future solar systems, the very cradles where planets will one day coalesce. But the starburst creates a wide spectrum of suns. Alongside modest, long-lived stars like our own, it forges monstrous, short-lived giants. These massive stars burn through their nuclear fuel in only a few million years, a fleeting moment on the cosmic clock. Their lives end not with a whimper, but in cataclysmic supernova explosions that blast newly forged elements far into space. This is where the true alchemy of the merger happens. Within the hearts of those short-lived giant stars and in their violent deaths, the raw, simple elements of hydrogen and helium are fused into the building blocks of complexity. Carbon, oxygen, iron, silicon, all the essential ingredients for rocky planets, for water, and for life itself, are forged in these stellar furnaces and scattered by these titanic blasts. The starburst phase, for all its apparent violence, is fundamentally creative. It floods the galactic landscape with light and energy, but more importantly, it seeds the environment with the heavy elements necessary for a new generation of worlds. The ignition of countless new suns from the wreckage of old structures is the universe's most powerful demonstration that from chaos, new order can always emerge. Yet behind this brilliant firestorm of creation lies the universe's greatest hidden architect. Dark matter, the invisible scaffolding that binds the cosmos, dictates every step of this chaotic dance. Though we cannot see it or touch it, its gravitational presence is the true director of the merger. Long before the stars and gas we see begin their slow waltz, the vast halos of dark matter surrounding each galaxy have already intertwined. These halos, immense spheres of invisible particles, merge first, creating a deep, unified gravitational well. This unseen structure acts like a cosmic mold, pulling the visible components of stars and gas into its predetermined shape. Think of it as an invisible hand gently guiding two swirling clouds of glitter into a single, new form. The glitter represents the stars we see, but the hand is the dark matter, doing the real work of shaping the final structure. This is why the beautiful chaos of a merger follows a predictable pattern. The dark matter does not collide or smash like normal matter. Its particles simply pass through one another, interacting only through gravity. Yet this ghostly gravitational pull is enough to orchestrate the entire event, steering the visible galaxies on their collision course and ensuring they do not simply fly apart. The distribution of this dark matter halo is crucial. A dense, concentrated core can funnel gas inward at a ferocious rate, fueling intense starbursts and feeding the central black holes. A more diffuse halo might result in a slower, more drawn-out merger, producing a gentler transformation. Without accounting for this invisible actor, our most powerful computer simulations would fail. The visible wreckage we observe would never coalesce into the stable, elegant galaxies we see in the night sky. So while we watch the brilliant birth of new stars and the violent awakening of black holes, we are merely witnessing the actors on a stage. The dark matter has built the theater and written the script, its gravitational hand guiding the chaos toward a new cosmic order. This violent relaxation does not just rearrange the stars, it erases the very identity of the original galaxies. The beautiful, orderly rotation that defined them as majestic spirals is gone, replaced by a swarm of stars moving on random, chaotic paths. The final product of this cosmic overhaul is often something entirely new and surprisingly featureless, an elliptical galaxy. Picture a vast, glowing football or a fuzzy sphere of ancient suns, a celestial beehive where every star follows its own independent orbit. There are no spiral arms, no bright lanes of gas and dust, just a smooth, golden haze of countless stars. This transformation from a structured disk to a formless ellipsoid is one of the universe's most dramatic makeovers. The reason lies in the physics of the merger itself. As billions of stars are violently flung about by the changing gravitational field, they lose their collective memory of spinning in a neat disk. Their orbits are randomized, a process astronomers call violent relaxation. The end result is a system where stars no longer circle a common center in a single plane. Instead, they buzz around the galactic core in every direction imaginable, creating the smooth, three-dimensional shape of an elliptical. This new galaxy is not just structurally different, it is also a quieter, older place. The merger process that created it was so energetic that it either used up all the available gas in a final, glorious starburst, or it expelled the remaining gas reservoirs out into intergalactic space. With little cold gas left to collapse, the frantic birth of new stars grinds to a halt. The brilliant blue nurseries fade away, leaving behind the longer-lived, older, and redder stars. The galaxy enters a long, slow autumn, its days of dramatic change largely behind it. We see evidence of this profound transition when we look deep into space and therefore far back in time. Distant galaxy clusters, which we see as they were billions of years ago, are filled with a much higher proportion of these elliptical galaxies. This tells us that in the crowded, violent early universe, such mergers were the rule, not the exception. The birth of an elliptical from the wreckage of spirals is not a random accident. It is a fundamental life cycle event, a testament to how gravitational encounters can permanently alter the fate of an entire island of stars, closing one chapter of cosmic history while quietly opening the next. This cosmic dance is not just a spectacle happening in the distant universe. It is our own galactic destiny. The Milky Way and its colossal neighbor, the Andromeda Galaxy, are already falling toward one another, set to meet in about 4.5 billion years. We are not mere observers of this process. We are future participants. Precise measurements from the Hubble Space Telescope have removed all doubt. The two galaxies, drawn together by their mutual gravity, are locked in a flight path that will end in a magnificent merger. The familiar band of the Milky Way arching across our night sky will be utterly transformed. What will this mean for our solar system? The vast emptiness of space is our greatest protector. Even during the most violent phases of the merger, the actual risk to our Sun and its planets is remarkably low. The average distance between stars in a galaxy is so immense that direct collisions are extraordinarily rare. Our solar system will almost certainly not be torn apart. Instead, it will likely be gravitationally flung onto a new, wild orbit, sent hurtling through the evolving chaos of the merging galaxies. We will be passengers on a thrilling ride through a cosmic construction zone. From our vantage point, the sky would become a canvas of unprecedented change. The serene spiral of Andromeda, currently a faint smudge of light, would grow larger and more detailed with each passing million years. As the galaxies make their first close pass, their structures would warp and distort, filling the heavens with immense streams of stars and glowing gas. The tranquil darkness would be banished, replaced by a brilliant, ever-shifting tapestry of light. The final product of this billion-year-long process will be a new, singular galaxy. Astronomers have already given this future giant a name, Milkdromeda. It will likely be a massive elliptical galaxy, a smooth, golden hive of stars, a testament to the violent relaxation that erased the spirals we call home. This merger will dominate our local group of galaxies, creating a titan that will stand alone for eons to come. For scientists, this impending event offers an unparalleled opportunity. We are like residents of a coastal town who have studied tsunamis from afar, only to now learn that one is heading directly for us. We can calibrate our models and test our theories against a cataclysm unfolding in our own backyard. The merger of the Milky Way and Andromeda provides a humbling, long-term perspective. It reminds us that the cosmos is not a static painting but a dynamic, ever-changing arena of creation and destruction. Our entire history, from the first single-celled organism to the rise of human civilization, is but a single, fleeting moment in the grand timeline of our galaxy's life. While the chaotic merger often forges a smooth elliptical giant, sometimes the cosmic crash yields a more intricate sculpture. A direct bullseye collision can give birth to one of the universe's most stunning formations, a ring galaxy. This happens when a smaller galaxy, like a cosmic bullet, punches straight through the heart of a larger spiral disk. The gravitational shock wave from this piercing impact does not shatter the larger galaxy. Instead, it sends a ripple of compressed gas and dust racing outward, like a wave expanding across a pond. This propagating density wave triggers a firestorm of star formation in a near-perfect circle, leaving the central core of the larger galaxy relatively untouched and seemingly floating inside a brilliant star-studded hoop. The Cartwheel Galaxy is the quintessential example. Its spectacular wheel-like appearance a clear and recent scar from a direct hit. For a few 100 million years, it will glow as a perfect cosmic bullseye before the ring slowly disperses. Other mergers sculpt different forms of temporary art. As immense tidal tails are pulled out during the interaction, they can drag vast amounts of gas and dust with them. Within these colossal streams of debris, the density can become so high that the material collapses under its own gravity. From the wreckage flung out by the galaxies, new, smaller galaxies can coalesce. These are tidal dwarf galaxies, entirely new stellar systems born from the discarded material of their parents. They are cosmic phoenixes, rising from the gravitational ashes of the collision. Many will remain as satellite galaxies, while others might even become fully independent, embarking on their own cosmic journeys. These peculiar structures, whether perfect rings or newborn dwarfs, are fleeting cosmic sculptures. They shine with incredible brilliance for a few 100 million years, a mere blink in galactic timescales before they are either absorbed back into their parent galaxy or simply fade away as their star formation fuel is exhausted. For astronomers, they are more than just beautiful accidents. They provide natural laboratories, allowing us to observe the laws of physics, conducting extreme experiments in star formation and galactic evolution. The sheer diversity of forms that can emerge from these collisions, from smooth ellipsoids to perfect rings, highlights the boundless creativity of gravitational physics. It shows us that the universe, in its chaos, is not just a destroyer but a master artist, capable of sculpting an endless gallery of celestial wonders from the simple pull of gravity. This frantic starburst phase comes with a spectacularly violent echo. For every brilliant, massive star born in the chaos, a supernova is almost guaranteed to follow. These are not random disasters but the direct, explosive consequence of the merger's creative fury. Massive stars live fast and die young, burning through their nuclear fuel in just a few million years before collapsing in cataclysmic blasts that can briefly outshine an entire galaxy. In a merging galaxy, this process is amplified from a sporadic event into a constant, rolling thunder. The rate of supernova explosions can surge to hundreds of times higher than in a quiet, isolated spiral like our own Milky Way. The sky of a world inside such a galaxy would be a terrifyingly beautiful spectacle, lit by the frequent, temporary fire of new suns being born and old ones dying. Each of these titanic explosions is far more than a final flash of light. It is a fundamental act of cosmic alchemy, deep within the cores of massive stars and in the unimaginable pressures of their supernova deaths. The universe forges the elements of complexity. The simple, primordial hydrogen and helium are fused into heavier atoms. Oxygen, carbon, silicon, and iron are cooked in these stellar furnaces and then blasted outward at nearly the speed of light. These newly forged elements are scattered like cosmic seeds, enriching the vast clouds of gas and dust that swirl between the stars. This chemical enrichment is the single most important step for building a world like our own. Without it, the interstellar medium would remain a barren soup of hydrogen and helium, incapable of forming the rocky, metallic cores of terrestrial planets. There would be no carbon for organic molecules, no oxygen for water, no iron for a planetary core. The very stuff of our planet and our bodies was forged in the hearts of stars that lived and died during such periods of intense galactic activity. This cycle of destruction and creation generates a powerful feedback loop that shapes the entire galaxy. The shock waves from countless supernova rip through the surrounding gas clouds. These waves are like cosmic tsunamis of energy, compressing some regions to trigger yet another wave of starbirth, while simultaneously heating and dispersing other gas reservoirs, effectively shutting down star formation in those areas. It is a self-regulating system, a celestial boom and bust cycle driven by stellar life and death. The merger, therefore, does not just build stars, it builds the very periodic table of elements. It transforms a simple, pristine universe into a chemically rich and diverse one, setting the stage for the eventual formation of complex planets and the potential for life. The iron in your blood, the calcium in your bones, and the oxygen you breathe are all souvenirs from a long-ago star that died in a cataclysm, perhaps during the very merger that helped to build our cosmic home. At the very heart of this galactic chaos, the two supermassive black holes begin their final, fateful dance. Having been stirred from their slumber, these cosmic monsters, each weighing millions or even billions of times more than our Sun, now drift toward the center of the new, combined galaxy. They do not fall straight in. Instead, they sink slowly through a process called dynamical friction. As they plow through the dense thicket of stars at the galactic core, their immense gravity pulls stars toward them, creating a stellar wake. This gravitational drag acts like a cosmic brake, steadily sapping their orbital energy and causing them to spiral ever closer to the center. Over millions of years, their separate paths converge until they are locked in a mutual orbit, becoming a binary black hole system. These two titans now circle one another, their gravitational bond dictating the rhythm of the entire galactic core. Their dance is not a gentle one. As they whirl around their common center of gravity, they act like a pair of unimaginably powerful gravitational slingshots. Any star that ventures too close on a random orbit can be violently flung away at tremendous speeds, ejected entirely from the galactic nucleus. This stellar cleansing gradually thins out the core, creating a region of lower density around the binary pair and fundamentally altering the structure of the galaxy's very heart. For eons, this binary system can orbit, its members separated by a distance no greater than our own solar system. The end game of this cosmic waltz is the most energetic event in the universe since the Big Bang. As the black holes continue to lose energy, they spiral inward faster and faster, finally merging into a single, more massive black hole. This final collision does not produce a flash of light in the traditional sense. Instead, it unleashes a storm of gravitational waves, powerful ripples in the very fabric of spacetime itself. These waves propagate outward at the speed of light, carrying with them the signature of this colossal merger. Observatories like LIGO and Virgo are specifically designed to detect these faint echoes from such catastrophic events, listening for the cosmic tremors that confirm our most dramatic predictions about gravity. Sometimes, however, the merger is not completely dark. If a significant amount of gas remains in the galactic core, it can be drawn into an accretion disk around the binary black holes. As the black holes orbit, they can periodically disturb this gaseous disk, causing it to glow brightly at predictable intervals. This creates a flickering beacon of electromagnetic radiation, a brilliant periodic flare that offers astronomers another way to witness and study these elusive dances. The fate of supermassive black holes in a galactic merger provides a unique window into the most extreme gravitational environments imaginable, places where the laws of physics are pushed to their absolute limits. The ultimate fate of a planet during a galactic merger depends on its cosmic address. For a world orbiting a star in the quiet galactic suburbs, far from the crowded core, the Great Merger may pass as a spectacular light show with little direct danger. But for planets born in the dense stellar cities near the galactic center, the event is an existential threat. The primary danger comes from gravitational perturbations. As stars are flung onto new, chaotic paths, close encounters become frighteningly common. A passing star's gravity can act as a cosmic tug, subtly or violently altering a planet's orbit. A world once perfectly positioned in its star's habitable zone could be flung into the frigid darkness of interstellar space, becoming a permanent rogue planet. Alternatively, the perturbation could send it spiraling inward on a death plunge into its parent star. The stability that life likely requires to evolve over billions of years is shattered in an instant of gravitational mischief. Beyond orbital chaos, the sky itself becomes a source of peril. The intense radiation from nearby supernova explosions and the fierce glare of an awakened quasar at the galaxy's core bathe planets in lethal doses of high-energy particles and ultraviolet light. A world with a protective magnetic field and a thick atmosphere might withstand the assault, though its ozone layer could be devastated. A thinner atmosphere, like that of Mars, could be entirely stripped away, leaving a barren rock exposed to the harshness of space. For any complex life that may have arisen, this period would be an unsurvivable extinction-level event, a sterilization on a galactic scale. Yet, in a profound demonstration of cosmic balance, the very forces that destroy old worlds are simultaneously building new ones. The colossal clouds of gas and dust, freshly enriched with heavy elements from supernova, become the nurseries for a new generation of stars and planets. The violent compression of these clouds during the merger triggers not just star formation, but an accompanying burst of planet formation. The protoplanetary disks swirling around infant stars in these chaotic environments are far richer in carbon, oxygen, silicon, and iron than the disk that formed our own solar system. This abundance of heavy elements provides more raw material to build terrestrial, Earth-like planets, and to seed them with the water and organic molecules essential for life. This leads to a fascinating and counterintuitive possibility. While a merger undoubtedly devastates habitable zones in the short term, it may dramatically increase the total number of habitable worlds across the galaxy over billions of years. By flooding the interstellar medium with the necessary ingredients, galactic collisions might be a crucial mechanism for enhancing the overall habitability of the universe. The destruction of one generation of planets paves the way for the next, potentially more numerous and better equipped for life. The galaxy, it seems, understands that sometimes you must tear down the old neighborhood to build a new, and possibly even grander, cosmic metropolis. Beyond the titanic pull of gravity and the flash of stellar fire, another invisible force is quietly shaping the chaos. Immense magnetic fields, woven through the very fabric of interstellar space, are active participants in the galactic drama. These fields are not mere spectators. They are frozen into the ionized gas that drifts between the stars, and when galaxies collide, this magnetic tapestry is stretched, twisted, and amplified to incredible strength. Think of it as pulling on a tangled bundle of rubber bands. The more you stretch and contort them, the more tension and structure they develop. During a merger, the same gravitational forces that pull out tidal tails also pull on these magnetic field lines, concentrating their power and weaving them into new, ordered patterns. This magnetic reinforcement can act in two seemingly opposite ways. In some regions, a strengthened magnetic field creates a supportive pressure that helps gas clouds resist gravitational collapse, putting a temporary brake on the birth of new stars. In other areas, the twisted fields can actually assist star formation by helping the gas shed its spin. As a vast cloud collapses, it needs to lose its rotational energy to shrink further. The magnetic fields act like cosmic brakes, transferring that spin away and allowing the cloud to condense more efficiently into a new sun. Radio telescopes give us a unique view of this hidden architecture. They do not see the stars or the glowing gas, but they can map the synchrotron radiation emitted by cosmic ray electrons spiraling along these magnetic field lines. In several famous mergers, these observations reveal breathtakingly organized patterns. Vast magnetic fields can be seen tracing the sweeping arcs of tidal tails or forming a coherent structure throughout the new galactic core, a silent testament to the order emerging from the chaos. This intricate interplay between gravity and magnetism adds a crucial layer of complexity to our understanding. It reminds us that the evolution of a galaxy is not dictated by a single force, but by a symphony of them, where even the most subtle players can guide the construction of new worlds. The entire life cycle of a galactic merger unfolds on a timescale that dwarfs human history. A typical collision, from the first faint gravitational whisper to the final serene stability, spans well over 1 billion years. It begins with the initial approach, a slow cosmic courtship where two galaxies, drawn by their mutual gravity, spend hundreds of millions of years simply closing the vast distance between them. During this prolonged approach, the first subtle signs appear. Their perfect spiral arms begin to warp and stretch, pulled out of shape by a force they cannot yet touch. This is a patient, almost imperceptible prelude to the chaos that will follow. Then comes the real dance. The galaxies make their first close pass, swinging by each other in a gravitational slingshot that unleashes the full spectacle. Tidal tails are ripped out, stellar nurseries ignite, and the structures of both galaxies are torn asunder. This dramatic phase of multiple close encounters, where the most visible reshaping occurs, can last for several 100 million years more. Within this extended period of turmoil, the most intense creative fire burns surprisingly fast. The peak of the starburst activity, that frantic explosion of new suns, may blaze for only a few tens of millions of years. On a cosmic clock, this is a fleeting, brilliant flash. It is a short, violent burst of construction that forges the majority of the merger's new stars and scatters the heavy elements for future planets. After the two galactic cores finally coalesce and the supermassive black holes at their hearts begin their own final dance, the new galaxy enters its long autumn. This phase is known as violent relaxation, a period where billions of stars, flung onto chaotic paths, slowly settle into their new, stable orbits within the combined gravitational field. This smoothing out process is not quick. It can take several billion years for the galaxy to finally relax into its permanent shape, whether that be a smooth, elliptical, or some other hybrid form. The entire sequence is a humbling lesson in cosmic patience. We can never watch a single merger from start to finish. Instead, astronomers piece together this billion-year timeline like detectives at a crime scene, studying countless snapshots of different mergers, each frozen at a different stage of evolution. By comparing a galaxy just beginning its first pass with another in the throes of a starburst and a third that is a relaxed elliptical, we can assemble the complete story of creation from cosmic chaos. The final shape of a galactic collision is not predetermined by chaos alone. It is the unique identity of each galaxy that writes the final chapter. The mass of the participants is the most decisive factor. When two giants of nearly equal size collide, it is a true battle of titans. Their gravitational influence is so perfectly balanced that neither structure can dominate. The resulting gravitational turmoil is so extreme that it completely erases their original forms. almost always forging a new, smooth, elliptical galaxy from the wreckage. This is known as a major merger, the ultimate cosmic restructuring event. But when a small galaxy is consumed by a much larger one, the outcome is far less dramatic. In this minor merger, the gravitational pull of the dwarf galaxy is simply too weak to seriously disrupt the grand design of its massive host. The larger galaxy's spiral disk can remain largely intact, absorbing the smaller system stars and gaining a faint, ghostly halo of new stellar streams as the only evidence of its cosmic meal. The fuel available for star formation is another critical ingredient. Galaxies brimming with cold hydrogen gas are like cosmic tinderboxes. When they collide, the gravitational disturbance acts like a match, igniting a ferocious firestorm of new stars. The more gas they contain, the brighter and more intense the resulting starburst will be. Conversely, when two gas-poor elliptical galaxies merge, the event is a quiet, almost ghostly affair. With little fuel left to compress, there is no brilliant burst of blue light, no frantic birth of new suns. The merger is a purely gravitational rearrangement of ancient red stars, a silent dance in the dark. Even the internal architecture of a galaxy can steer the collision's course. A galaxy with a strong central bar, a dense lane of stars cutting through its core, acts like a cosmic funnel. During a merger, this bar can efficiently channel gas inward toward the central black hole, feeding brilliant quasar activity. The angle of impact matters too. A direct bullseye collision can create a perfect ring galaxy, while a glancing, sideways blow might produce long, graceful tidal tails without completely destroying the spiral structure. This is why no two galactic mergers are ever truly identical. Each is a custom-built experiment in gravity, a unique combination of mass, fuel, and form that produces a one-of-a-kind celestial sculpture. This incredible diversity is not just beautiful, it is the key that allows astronomers to decode the entire life story of galaxies, reading the history of the universe in the endless variations of its collisions. This luminous transformation at the heart of a merger is one of the universe's most energetic displays. Galactic collisions are the ultimate trigger, flipping the switch on dormant supermassive black holes and turning them into active galactic nuclei. An active galactic nucleus is simply the intensely bright, compact region at the center of a galaxy where a supermassive black hole is actively feeding. As the merger funnels colossal amounts of gas and stars toward the galactic core, this material does not fall directly into the black hole. Instead, it forms a seething, flattened disk of superheated matter, an accretion disk that spins at nearly the speed of light. Friction within this disk heats it to millions of degrees, causing it to glow with a ferocious intensity that can outshine every single star in the host galaxy combined. For a brief cosmic moment, this single point of light becomes a quasar, a beacon visible across the universe. The specific type of brilliance we see depends on our viewing angle. If we look directly down the powerful jets of energy that often erupt from the poles of the black hole, we might classify it as a blazing quasar. If we view it from the side, partially obscured by dust, we might see it as a slightly less luminous but still formidable Seyfert galaxy. These are not different monsters, merely different faces of the same phenomenal engine, all powered by the gravitational chaos of a merger. The energy released by this feeding frenzy is not contained. It erupts outward, driving colossal winds that race through the galaxy at thousands of kilometers per second. These are not gentle breezes but tsunami-force outflows of gas and radiation, powerful enough to blast a galaxy's remaining star, forming fuel deep into intergalactic space. This process, known as AGN feedback, is a crucial cosmic regulatory mechanism. It is the universe's way of putting a hard stop to runaway star formation. The very same collision that ignited a firestorm of new stars can, through the black hole it awakens, eventually quench that fire forever. This intimate link between the vast scale of a galactic merger and the pinpoint fury of a black hole reveals a profound truth. The evolution of a galaxy is not governed by a single force, but by a delicate, interconnected dance between gravity, star formation, and the awesome power unleashed from its very heart. These smallest cosmic islands are the true silent majority of the universe, dwarf galaxies, far more numerous than their majestic spiral cousins, are the pawns in the grand chess game of galactic collisions. Their fates are not their own, but are instead dictated by the gravitational storms unleashed when giants collide. A dwarf galaxy orbiting a large spiral is like a small moon tethered to a planet. When that planet collides with another, the moon's peaceful orbit is shattered. The immense and shifting gravitational tides from the merging giants can pull the dwarf apart, stretching it into long, faint streams of stars that are eventually absorbed, adding silently to the larger galaxy's halo. This process is a form of cosmic accretion, a quiet consumption that has built up the largest galaxies over billions of years. Yet, for some of these dwarfs, the chaos presents a fleeting opportunity. As the massive galaxies churn, they can compress the gas within a nearby dwarf galaxy, triggering a sudden, brilliant burst of star formation. A small, unassuming blob of stars can suddenly blaze with the blue light of newborn suns, experiencing a creative renaissance directly caused by the destructive forces nearby. This borrowed time is often short-lived. The same gravitational forces that gifted the dwarf with new stars can just as easily strip away its gas reservoirs, the very fuel for its future. Robbed of this material, the dwarf galaxy cannot form new stars. Its population ages and reddens, and it slowly fades into a dark, fossilized relic, a ghost of a galaxy whose potential was extinguished by the cosmic turmoil. This dual nature of creation and destruction underscores a fundamental cosmic model. The hierarchical structure of the universe suggests that every giant galaxy we see, including our own Milky Way, was assembled over eons from the cannibalization of countless smaller dwarfs. These tiny galaxies are the primordial building blocks, the cosmic bricks and mortar from which the grandest cathedrals of stars were constructed. By studying how they survive or perish in the violent neighborhoods of merging galaxies, we are essentially reading our own deep history. Their fate is a proxy for the ancient events that built our home, revealing that even the largest structures owe their existence to the accumulation of the smallest ones. But to truly understand this cosmic chaos, we must peer into the hidden physics of the gas itself. The grand dance of stars is choreographed by gravity, but the fiery birth of new suns is a story written in fluid dynamics. The interstellar medium is not empty space. It is a turbulent, wispy ocean of hydrogen and helium, a fluid that can be shocked, heated, and compressed. To unravel its behavior during a collision, astronomers rely on incredibly sophisticated tools known as hydrodynamical simulations. These are not simple animations. They are complex virtual universes governed by the same laws of physics that shape real galaxies, running on some of the world's most powerful supercomputers. These simulations treat the vast clouds of gas as a fluid, modeling how they slam into one another during a merger. When two galaxies intertwine, their gaseous disks do not pass through each other peacefully. They collide at phenomenal speeds, generating immense shock waves that ripple through the interstellar ocean. The simulations show these shocks heating the gas to millions of degrees, causing it to glow in X-rays. But then, another crucial process begins. This superheated gas radiates its energy away, cooling down over thousands of years. As it cools, it loses the internal pressure that was holding it up, and it collapses under its own weight. This cycle of shock, radiate, and collapse is the fundamental engine of star formation in a merger. It is the reason why vast, dark clouds of inert gas can suddenly ignite into brilliant stellar nurseries. The virtual models track more than just motion and temperature. They are also cosmic alchemy labs. As the simulation runs, it accounts for the life cycles of the massive stars born in the chaos. When these stars explode as supernova, the simulation injects newly forged heavy elements like oxygen and iron back into the surrounding gas. This enriches the interstellar medium, polluting it with the very ingredients needed to form rocky planets in the next generation of stars. We can watch in an accelerated digital reality as a galaxy's chemical composition evolves from primordial simplicity to the rich complexity required for life. The power of these simulations lies in their ability to recreate the specific structures we see through our telescopes. With enough computing power, a model can start with two pristine spiral galaxies, set them on a collision course, and then sit back as the virtual laws of physics take over. The simulation will spontaneously generate sweeping tidal tails, brilliant starburst rings, and concentrated nuclear star clusters, mirroring the exact features observed in real systems like the antennae galaxies. This is the ultimate test, when a simulation built only on our understanding of fundamental physics can produce a galaxy that looks just like one in a Hubble image. We know our theories are on the right track. By constantly comparing these digital universes with real telescope data, astronomers can refine their ideas about star formation and the powerful feedback processes that regulate it. They can ask what-if questions that the real universe takes too long to answer. What if the galaxies collided at a different angle? What if one had more gas? The simulation becomes a digital laboratory, an indispensable crystal ball that allows us to replay the universe's most dramatic events and finally decipher the complex physics hidden within the beautiful chaos. This wealth of data does not come from a single viewpoint. Our understanding of galactic collisions is pieced together by observing the cosmos through many different eyes, each tuned to a specific slice of the electromagnetic spectrum. The iconic images from the Hubble Space Telescope have defined these events for a generation, capturing the intricate ballet of stars and dust in stunning visible light. We see the grand, sweeping arcs of tidal tails and the brilliant blue knots of star clusters, a breathtaking portrait of cosmic chaos. Yet visible light only tells part of the story. To peer into the heart of the storm, we need vision that can cut through the obscuring dust clouds. Infrared observatories like the Spitzer Space Telescope and its mighty successor, the James Webb Space Telescope, act as cosmic heat vision goggles. They see the warm glow of dust itself, heated by the furious birth of new stars hidden within. What appears as a dark, dusty knot in a Hubble image often blazes with the intense infrared light of a hidden stellar nursery in a JWST view, revealing the true, ferocious scale of the starburst. Meanwhile, giant radio dishes on the ground map the distribution of cold, neutral hydrogen gas. This is the raw, unformed fuel for future stars, and these observations show us how this primordial material is violently wrenched and contorted during the collision, channeled into the regions where new suns will ignite. At the other extreme of the energy scale, space-based X-ray observatories like Chandra detect the superheated gas. They see the multimillion-degree plasma created by colossal shock waves from colliding gas clouds and the fierce outflows from active supermassive black holes. Each wavelength of light is a different thread in the tapestry. The optical reveals the stars, the infrared unveils the hidden birth, the radio traces the fuel, and the X-rays expose the violent heat. Only by weaving all these threads together can astronomers build a complete, three-dimensional picture of the merger process. This multi-wavelength approach transforms a beautiful snapshot into a dynamic story. It confirms beyond any doubt that these titanic encounters are not rare cosmic accidents, but a common, fundamental, and transformative force that has shaped the universe we see today. These galactic collisions are not isolated accidents. They are the local expressions of a pattern woven across the entire observable universe. Galaxies are not scattered randomly through the void. Instead, they are arranged in a vast cosmic web, an immense architecture of light and dark matter. This web consists of long, dense filaments where galaxies cluster like pearls on a string, immense clusters where hundreds of galaxies swarm in a chaotic ball, and vast, empty voids that stretch for hundreds of millions of light years, the desolate deserts of the cosmos. It is within the densest knots and filaments of this web that galactic mergers happen most frequently. In the crowded environment of a galaxy cluster, the constant, close gravitational encounters between galaxies are like cars on a busy highway, making collisions and near misses a common part of cosmic life. The grand driver of this entire structure, from the largest void to the smallest dwarf galaxy, is the invisible hand of dark matter. From the earliest moments after the Big Bang, slight fluctuations in the density of dark matter began to act as gravitational seeds. Over billions of years, ordinary matter, the gas that would form stars and planets, was pulled into the growing gravitational wells created by these dark matter halos. Think of the cosmic web as a mountain range, and dark matter is the underlying tectonic plate that shapes the peaks and valleys. The visible galaxies are merely the snow-capped peaks, the most obvious features on a much larger, unseen foundation. This process is known as hierarchical structure formation. The universe did not build its largest galaxies first. It started small. Tiny dark matter halos merged to form larger ones, which then pulled in dwarf galaxies, which then collided to form the majestic spirals we see today. Every major merger we have discussed is simply a later chapter in this ongoing story of cosmic assembly. The chaotic dance of two spiral galaxies is just the universe following its fundamental blueprint, a blueprint written in the gravitational language of dark matter. This understanding gives cosmologists a powerful tool. By observing the rate and outcomes of galactic mergers, and by mapping the large-scale structure they help to create, scientists can run the universe in reverse. They can test their most fundamental models of how dark matter behaves. Does it move fast or slow? Do its particles interact with each other beyond gravity? The specific way that galaxies cluster into filaments and merge into giants provides the answers. The beautiful, violent chaos of colliding galaxies is not just a spectacle. It is a crucial piece of evidence, a dynamic laboratory that helps us decode the hidden rules governing the cosmos itself. Our current window into the cosmic dance of galaxies is about to be thrown wide open. A new generation of observatories, designed with capabilities that dwarf today's telescopes, stands ready to transform our view of galactic collisions from a series of beautiful snapshots into a dynamic, high-definition movie. The Vera C. Rubin Observatory, currently under construction in Chile, will perform an unprecedented decade-long survey of the entire southern sky. Its enormous mirror and massive camera will not just find thousands of merging galaxies, it will capture millions, allowing us to see them at every conceivable stage of their evolution, from the first faint tidal distortions to their final, serene forms. This colossal statistical sample will let us answer fundamental questions with precision. How did the rate of galactic collisions change as the universe aged? Do certain types of mergers dominate in specific cosmic environments? For the first time, we will move beyond studying individual oddities to understanding the population as a whole. While the Rubin Observatory scans the sky in visible light, other giants will listen and look in different ways. The Square Kilometre Array, a radio telescope network spanning 2 continents, will map the distribution of cold hydrogen gas in and around countless merging systems. This will reveal the invisible fuel for star formation, showing us exactly how gravity funnels this raw material into the violent starbursts that light up the cosmos. Simultaneously, the Nancy Grace Roman Space Telescope, with a field of view 100 times larger than Hubble's, will peer deep into the infrared universe. It will cut through the dust that obscures the earliest stages of galactic encounters, witnessing the birth of the very first massive galaxies in the ancient universe, systems that were likely built by a frenzy of mergers in the cosmic dawn. Perhaps the most profound shift will come from listening to the universe in an entirely new way. These observatories will work in concert to identify the most promising candidates for supermassive black hole binaries, pairs of these cosmic monsters spiraling toward their final collision. As they inch closer, they stir the fabric of spacetime itself, generating faint ripples known as low-frequency gravitational waves. A new era of space-based gravitational wave observatories, like the proposed LISA mission, is being designed specifically to detect these deep cosmic tremors. The detection of these waves will not be a rare event, but a routine census of the final, violent moments of black hole mergers across the universe. This will provide a direct, unambiguous signal of these titanic unions, completely independent of the light they emit. This coming flood of data will not simply confirm our existing models, it will almost certainly break them. The universe, when observed in such exquisite and comprehensive detail, always reveals new phenomena that challenge our neatest theories. We will likely discover entirely new classes of interacting galaxies, or witness feedback processes between stars and black holes that we never imagined. The next decade of discovery will push our understanding of galactic evolution into uncharted territory, forcing us to refine our simulations and rethink our assumptions. The chaotic beauty of colliding galaxies has captivated us for decades, but we are now on the cusp of truly understanding the intricate physics that governs their creation, a journey that will reveal not just the history of other galaxies, but the complete story of our own cosmic home. These cosmic collisions force a profound shift in our perspective on chaos itself. We often see chaos as an agent of pure destruction, a disruptive force to be feared and resisted. But the universe presents a different story, one where chaos is the essential engine of creation. The violent merger of 2 galaxies is not an aberration in a quiet cosmos. It is a fundamental, cyclical process where the old must be dismantled to make way for the new. From the apparent turmoil of colliding gas clouds and shattered stellar orbits, a new galactic structure emerges, one that is stable, ordered, and capable of hosting new generations of worlds. This cosmic principle mirrors patterns we see all around us. A forest fire, for all its terrifying destruction, clears the way for new growth and enriches the soil. The constant churn of tectonic plates, which brings devastating earthquakes, also recycles the minerals essential for life and builds new continents. The universe seems to operate on a simple, powerful law. Creation requires the raw materials that only destruction can provide. Our very existence is a direct testament to this cycle. Every atom of oxygen in the air we breathe, every particle of iron in our blood, was forged in the heart of a massive star that lived and died violently, likely during a period of galactic upheaval billions of years ago. We are not just observers of this cosmic dance, We are literal stardust, the product of ancient chaos that has been recycled into conscious life. This realization carries a deep humility. The majestic spiral of the Milky Way, which seems so permanent in our night sky, is a fleeting structure. In a few billion years, its beautiful symmetry will be erased forever in a merger, transformed into a new type of galaxy. All galactic forms are temporary waypoints in an endless cycle of change. This cosmic transience invites us to see our own world, with its societal shifts and ecological transformations, as part of a much larger narrative of constant creative destruction. The same forces that build and rebuild galaxies are echoed in the evolution of life and the rise and fall of civilizations. By studying the grandest collisions in the universe, we are ultimately seeking wisdom about the nature of change itself, learning that resilience is not about resisting chaos, but about understanding our place within its creative, unending flow. The most arresting portraits of our universe are not painted by human hands, but by the violent brushstrokes of colliding galaxies. These cosmic landscapes, captured by powerful telescopes, have become iconic images that transcend pure science, sparking wonder in artists and the public alike. We see these magnificent swirls of gold and blue, these immense arcs of starlight, and we instinctively recognize a profound, chaotic beauty. Yet the vibrant colors we admire are often a scientific translation. Astronomers assign specific hues to different wavelengths of light, from the invisible glow of hydrogen gas to the fierce radiation of X-rays, to create a color-enhanced image. This process is not a deception, but a careful blend of empirical data and artistic interpretation, allowing our eyes to perceive the intricate physics that would otherwise remain hidden. It reveals a universe where the most violent processes can generate breathtaking splendor, where the shock waves that tear gas clouds apart also sculpt them into forms of stunning elegance. This hidden aesthetic dimension is brought directly to the public through immersive planetarium shows and museum exhibits. As you sit beneath a digital dome and watch two galaxies spiral into one another in a silent, slow-motion ballet, the complex concepts of tidal forces and star formation become intuitively understood. You are not just learning about gravity, you are feeling its immense creative power. This intersection of art and science does more than communicate facts. It enriches our cultural relationship with the cosmos. The same swirling patterns that govern a galactic merger can be found in abstract paintings and natural forms on Earth, suggesting a universal language of form and energy. The beauty of these collisions serves as a vital bridge, connecting the cold, hard data of empirical inquiry to the warm, boundless realm of human creativity, reminding us that our search for truth and our search for beauty are ultimately the same journey. The sheer number of galaxies in modern sky surveys presents a monumental challenge, one far too vast for any single team of professional astronomers to handle. This is where the power of collective human curiosity takes center stage. Projects like Galaxies Zoo have brilliantly tapped into this resource, inviting hundreds of thousands of volunteers from all over the world to become galaxy classifiers. With a brief online tutorial, anyone can begin sifting through stunning images from telescopes and start identifying the telltale signs of a cosmic crash. The human brain possesses an unparalleled ability for pattern recognition, often spotting the subtle gravitational distortions, faint tidal streams, and peculiar asymmetries that signal an ongoing merger, details that even the most sophisticated computer algorithms can sometimes overlook. This collaborative filter has proven incredibly fruitful, with citizen scientists discovering some of the most rare and bizarre interacting systems ever recorded. These peculiar finds are not just curiosities, they become immediate candidates for follow-up observations with the world's most powerful telescopes, adding crucial data points to our understanding of how these chaotic events unfold. This public participation does more than just accelerate the pace of discovery. It fundamentally transforms people from passive observers into active explorers. By spending a few minutes classifying a distant island of stars, a person becomes directly connected to the frontiers of cosmic knowledge, contributing to a collective effort that is mapping the evolving structure of our universe. The success of these initiatives stands as a powerful testament to what we can achieve when we work together, proving that the human eye, in its millions, remains one of astronomy's most valuable instruments for deciphering the beautiful chaos of colliding galaxies. These galactic collisions write their history directly into the stars themselves. We can read this ancient record through a field known as Galactic Archaeology, a science that pieces together a galaxy's past by studying the motions and chemical compositions of its countless suns. Just as an archaeologist on Earth might uncover the layers of a lost city, astronomers dig into the galactic disk and halo, searching for stellar artifacts that betray a violent past. The most dramatic of these fossils are the stellar streams. These are the ghostly remnants of smaller galaxies that were torn apart by our Milky Way's gravity, now stretched into long, shimmering rivers of stars that wrap around our galaxy like celestial ribbons. They are the final, fading signatures of ancient collisions, visible proof that our galaxy has grown by consuming its smaller neighbors. Beyond these obvious streams, there are more subtle clues. Astronomers find entire populations of stars moving in strange, synchronized orbits, all swimming against the orderly rotation of the main galactic disk. These kinematic anomalies are like a distinct accent in a crowded room, revealing a group of stars that originated elsewhere and were absorbed long ago. Their very motion is a memory of a different galactic homeland. Even the chemical makeup of a star tells a story. Stars born together in the same cosmic nursery share a similar chemical fingerprint, a specific ratio of elements like iron and hydrogen. When astronomers find a cluster of ancient stars with a unique chemical signature moving on a peculiar path, it is a clear signpost of a past merger. This is how we discovered the Gaia sausage, the remnants of a massive dwarf galaxy that smashed into the young Milky Way billions of years ago. That colossal impact is believed to have violently puffed up our galaxy's disk, contributing to the formation of what we now call the galactic thick disk. Every star, then, is a historical document. Its orbit is a record of the gravitational forces it has experienced, and its composition is a ledger of the elemental abundance in the cloud from which it formed. By reading millions of these stellar records, galactic archaeologists can rewind time, reconstructing the sequence of chaotic events that assembled our seemingly tranquil Milky Way. This forensic work reveals that our galactic home is not a pristine, isolated island, but a magnificent mosaic built from the wreckage of countless smaller galaxies over billions of years. The quiet spiral we see today is the peaceful aftermath of an ancient cosmic storm. The violent energy of a galactic collision does not remain confined to the stars. It radiates outward, reshaping the very emptiness between galaxies. This seemingly void space, known as the intergalactic medium, is not a perfect vacuum. It is a whisper-thin ocean of primordial gas, and when two galaxies merge, they send tsunamis crashing through it. The primary drivers are the powerful galactic winds launched by the frantic starburst and the awakened black hole. These are not gentle breezes but hurricane-force outflows, propelled by the combined energy of countless supernova explosions and the fierce radiation from the active galactic nucleus. These winds can reach speeds of thousands of kilometers per second, and they carry with them a precious cargo. They eject gas that has been freshly enriched with heavy elements like oxygen, carbon, and iron. the very elements forged in the hearts of stars and their explosive deaths. This process effectively pollutes the pristine intergalactic medium, seeding it with the building blocks for future planets and, potentially, life. It is a form of cosmic gardening on the grandest scale, where a galaxy's death throes fertilize the cosmic soil for generations to come. This exchange is a critical part of what astronomers call the Baryon cycle, the continuous circulation of normal matter between galaxies and their surroundings. The consequences of this pollution are profound. By ejecting enriched material, a merger can permanently alter the chemical future of an entire region of space. When a new galaxy eventually forms from this pre-polluted gas, it starts its life with a richer supply of heavy elements, allowing it to build rocky planets more efficiently from the very beginning. But the impact is not solely about enrichment. These colossal outflows also carry immense thermal energy, violently heating the surrounding intergalactic gas. This heating raises the pressure of the medium, making it more difficult for other, quieter galaxies in the vicinity to pull in fresh, cold gas from their surroundings. By doing so, a single major merger can effectively stifle the growth of its neighbors, putting a regulatory brake on star formation across a wide swath of the cosmic web. The chaos of a collision ripples outward, governing the growth of cosmic structures far beyond the two original galaxies. In the most crowded neighborhoods of the universe, like massive galaxy clusters, this effect is amplified. Here, the space between the galaxies is filled with a seething, superheated plasma known as the intracluster medium. When clusters themselves collide, or when a major merger happens within one, the resulting gravitational turmoil acts like a giant spoon, violently stirring this intracluster gas. The collisions create immense shock fronts and turbulence that ripple through the plasma, heating it to even more extreme temperatures. These disturbances are not invisible. Space telescopes like Chandra, which see the universe in X-rays, reveal these shock waves as vast, delicate ripples and sharp edges in the glow of the hot gas, like sound waves frozen in a cosmic fluid. This stirring has a direct consequence. It prevents the intracluster gas from cooling down and falling back onto the individual galaxies, effectively cutting off their primary fuel supply for making new stars. A merger, therefore, can orchestrate the final act for an entire community of galaxies, pushing them into a quiet, red, and dead retirement. The story of a galactic collision is never just about two galaxies. It is about how their explosive partnership changes the character of their entire cosmic neighborhood, weaving their fate into the larger tapestry of the evolving universe. Floating in the cosmic darkness are some of the universe's most elusive ghosts. These are ultra-diffuse galaxies, vast islands of stars so faint they have barely more substance than a cosmic rumor. They contain as many stars as a typical dwarf galaxy, but these suns are scattered across an area as large as the Milky Way, creating a surface brightness so dim it barely registers against the blackness of space. Spotting one is like trying to see a single, dimly lit light bulb from miles away. For a long time, these spectral objects simply slipped through our surveys, their faint glow lost in the glare of the night sky. Their existence poses a profound mystery. How can a galaxy be so large, yet possess so little light? The answer appears to be written in the subtle language of galactic collisions. Sophisticated computer simulations reveal a compelling origin story for many of these ghosts. When a small dwarf galaxy experiences a close gravitational encounter with a much larger neighbor, it does not always get completely consumed. Instead, the immense tidal forces can stretch it, pulling its stars outward into a vast, diffuse cloud while stripping away the gas needed to form new, bright suns. The dwarf galaxy is not destroyed but transformed into a permanent, ethereal echo of its former self, a galactic silhouette stretched across the void. This tidal stretching offers a clean explanation for why these objects are so large and yet so dim. But the cosmos always enjoys a good plot twist. Another class of ultra-diffuse galaxy may have a completely different history. These could be failed galaxies, systems whose dark matter halos were massive enough to begin the process of formation, but whose internal gas was violently expelled. Powerful supernova explosions or fierce radiation from newborn stars could have blown the star-forming fuel away before it could collapse into many suns, leaving behind a dark matter scaffold populated by only a sparse, ancient stellar population. The discovery of these ghostly galaxies forces a fundamental reassessment of what a galaxy even is. They demonstrate that the outcomes of gravitational interactions are far more diverse than we ever imagined. It is not a simple binary of creation or destruction. A merger can forge brilliant starbursts and feed quasars, but it can also create these permanent, quiet shadows, these vast and silent realms that drift unseen through the cosmic web. Each one we find is a crucial clue, a testament to the subtle and lasting effects of a gravitational encounter, reminding us that the universe's grand collisions leave behind more than just giants. They also scatter the cosmos with gentle, fading whispers. Deep within the radio silence of space, a mystery unfolds in a single, blinding millisecond. Fast radio bursts are incredibly powerful pulses of radio waves that last less than the blink of an eye, and their origins have puzzled astronomers since their discovery. These cosmic flashes release more energy in 1,000th of a second than our Sun does in 3 days, yet they vanish without a trace, leaving behind only a ghostly signal in our telescopes. The leading suspects for creating such intense, fleeting events are magnetars, which are neutron stars with the most powerful magnetic fields in the universe. Picture the strength of a typical refrigerator magnet, then amplify it 1,000,000 billion times over. A magnetar's magnetic field is so intense it can literally warp the atomic structure of matter on its surface. And when this magnetic crust experiences a starquake, a sudden, catastrophic shift, it can unleash a titanic blast of radio energy across the cosmos. This is where the chaotic forge of galactic mergers enters the story. The same frantic starbursts that light up colliding galaxies produce an extraordinary number of massive, short-lived stars. These stars live fast and die young, ending their lives in core collapse supernova that leave behind dense, spinning remnants. In the turbulent environment of a merger, the conditions are perfect for creating not just ordinary neutron stars, but the extreme, ultramagnetic variety. The elevated rate of supernova in these stellar nurseries could dramatically increase the population of newborn magnetars, making a merging galaxy a potential factory for these enigmatic radio bursts. While a direct, confirmed link between a specific fast radio burst and a galactic merger remains elusive, the circumstantial evidence is compelling. Several repeating bursts have been traced back to galaxies that are actively forming stars, and some of these host galaxies show the distorted, irregular shapes suggestive of past or ongoing interactions. This correlation hints that the violent, creative processes at work during a collision might be the very trigger for these mysterious signals. If this connection solidifies, fast radio bursts would become more than just a cosmic curiosity. They would transform into powerful new tools for science. Each burst carries imprinted on its signal a record of all the material it has passed through on its journey to us. By studying these faint, millisecond-long whispers, astronomers could essentially use them as cosmic probes to map the distribution of invisible matter in the chaotic spaces between stars within a merging galaxy. The search for the source of these bursts adds a thrilling, modern layer to our investigation of cosmic chaos, turning ephemeral flashes into potential keys for unlocking the secrets of the universe's most dramatic transformations. These digital recreations of cosmic violence carry a profound ethical weight. When we build a simulation that shows two galaxies tearing each other apart, we are not glorifying destruction. We are using the most advanced tools at our disposal to decode the fundamental laws of physics. Every line of code in these virtual universes is written with a single purpose: to understand, not to celebrate catastrophe. The intent behind this research is purely constructive, aimed at illuminating the natural cycles that build everything we see. Our goal is to replace fear with a deep appreciation for the resilience woven into the fabric of the cosmos. This requires careful communication. We must always frame these events within their proper context, highlighting the creative outcomes. The same collision that shatters galactic structures also forges the stars and planets that become new cosmic homes. It is a story of transformation, not annihilation. Responsible science communication means presenting even the most violent phenomena as part of a grand creative cycle. By focusing on the birth of new suns and the seeding of heavy elements, we transform a narrative of chaos into one of endless potential. This ethical approach ensures that our exploration of the universe's most dramatic events remains a source of wonder, inspiring awe at the resilient and ever-creative nature of existence itself. The familiar constellations we know today will be long forgotten, their patterns scattered into an unrecognizable haze. In the new elliptical galaxy of Milkdromeda, the night sky will possess a profoundly different character. Gone are the majestic, dusty lanes of the Milky Way and the distinct spiral smudge of Andromeda. In their place, the heavens will be filled with a smooth, golden glow, a diffuse light from countless ancient, red stars that buzz in every direction like a swarm of cosmic bees. You will search in vain for the brilliant blue-white light of young stellar giants, for the frantic stellar nurseries that once blazed with new suns will have fallen silent, their fuel exhausted or expelled. The core of this new galaxy will be a quiet place, dominated by a single, dormant supermassive black hole, a sleeping leviathan that has consumed the available gas and now rests after its furious awakening. The gravitational landscape of our entire local group will be rewritten. Smaller galaxies like the Triangulum Galaxy and the Magellanic Clouds, which once orbited the Milky Way or Andromeda, will likely be drawn into the new giant, their stars absorbed to add to the golden halo or torn into faint, fading streams. This new galactic titan will stand alone, its gravitational influence dictating the motion of all remaining celestial bodies for trillions of years. Yet even in this seemingly static state, evolution continues. The era of dramatic change is over, but the slow, patient processes of the cosmos carry on. Milkdromeda may still experience minor accretion events, slowly consuming the few remaining, isolated dwarf galaxies that wander too close. Its population of stars will continue their own slow lives, with the longest-lived red dwarfs shining on for trillions of years, their faint light bathing any remaining worlds. This is the enduring legacy of a galactic collision, the final, stable form that can last for eons. It is a testament to the universe's cyclical nature, where violent chaos gives way to a long, serene autumn, a quiet and stable chapter in the endless story of cosmic change. Our journey reveals a universe where chaos is not the end, but a brilliant beginning. We have watched galaxies, those immense islands of stars, engage in a slow gravitational dance that forges new worlds from the wreckage of the old. This cosmic process teaches us that destruction and creation are not opposites, but two sides of the same coin, intertwined on a scale so vast it redefines our understanding of change. The birth of new suns in violent starbursts, the scattering of life-giving elements by supernova, and the final serene shape of an elliptical galaxy all testify to a universe that builds through upheaval. The insights we gain extend far beyond astronomy. They invite us to see the patterns of creative destruction echoed in our own world, from the rebirth of forests after a fire to the constant churn of tectonic plates that renew our planet. As we stand on the brink of a new era in astronomy, with powerful telescopes set to open unprecedented windows into the cosmos, we can anticipate discoveries that will further illuminate these majestic interactions. The story of colliding galaxies is ultimately our own story, written in stardust forged in ancient chaos. Let this exploration be a starting point for your own curiosity. The universe is a dynamic and ever-changing arena, and its greatest mysteries are still waiting to be uncovered. Subscribe for more journeys into the heart of space, and share your thoughts on these cosmic wonders in the comments below.